Hello everyone. We're here to present our developed work for the workshop de Agentes Físicos, WAF, for the year 2020. This work is titled Embedded Deep Learning Solution for Person Identification and Following with a Robot. The main objective of this work has been to build an autonomous robot that globally follows a person. And the available resources are an Nvidia Jetson TX2, which is an embedded system on module used for high performance computation, a Turtlebot2, which is an educational robotics set, as it can be seen on the figure on the right, and an Asus Axiom ProLive, which is an RGBD sensor. This extends a typical camera, providing additionally a depth image besides the RGB image of a typical sensor. The design of this system, the functionality, has been split into two main modules: the perception module and the actuation module. The perception module is composed of a 3 neural networks pipeline. These 3 neural networks evaluate sequentially an incoming image, passing it through 3 different networks. Firstly, we have the person detection neural network, which is based on a classical object detection convolutional neural network with the architecture SSD of a single shot multi-box detector. This detects the persons on the image. Later, we have the face detection network, which is a publicly available specific face detection neural network called FACET. This performs the same tasks than the previous network. However, this network is focused on detecting faces. And the last network is called FaceNet and is responsible of recognizing the faces, the found faces. This encodes the image of a face into a latent 128 latent space, as it can be seen in the figure on the right. On the other hand, TensorRT has been used to optimize these 3 neural networks. Later, the actuation module is responsible of implementing a reactive response on the robot. It makes use of a person tracker. This is based on an optical flow estimation method called Lucas-Canade algorithm, and is used to estimate the movement of a person between detections of the previously explained neural pipeline. This allows to implement a smoother response on the robot, and on the other hand, handling occlusions, because trusting directly in the outputs of the neural pipeline may lead into flickering detections in case the light conditions are not very friendly. Later, the controllers, 2 controllers have been implemented since the used robot has 2 degrees of freedom. On the one hand, it has a linear controller, which is responsible of going forward or backward, and on the other hand, the angular controller, which is responsible of turning the body of the robot in order to achieve another direction of going. So these controllers behave getting the person into what is called safe zones. On these safe zones, the robot doesn't need to move. However, if the person is not contained inside this safe zone, the robot has to move in order for the person being in that zone. These zones are evaluated using the error computation, which can be seen in the right middle figure. The angular error is computed directly on the person detection, subtracting the x coordinate from the center of the image, and the linear error is assessed using the depth image, sampling the region, the depth region inside the bounding box of the person, in order to find the distance from the robot to that person. So this is used to evaluate if the person is or not inside the safe zones. And if it is required, the robot will move itself. These movements are not directly sent to the motors, but they are passed through a closed loop control using a PID block. This allows to avoid overshooting and too slow responses. And the experimental results of the experiments conducted in this work allow to show several things. Firstly, the person detection network. Two architectures have been considered for this work. On one hand, the SSD controller, and on the other hand, the YOLO version 3 Tiny architecture. These graphs and this table show the results for each one of these methods. The inference time graph shows that the YOLO engine is capable of performing inferences at a much higher rate than the SSD network, since it takes much less time to make inferences. However, the intersection over union graph shows that the values of the intersection over union are more or less the same, but the YOLO graph, the YOLO blue line, shows many more gaps than the SSD one. This can be seen in the table below, where the detection rate of the YOLO-based network is only 17%, whereas the SSD one raises up to almost 74% of successful detections. So, although the YOLO framework takes much less time to infer than the SSD solution, the SSD solution is much more reliable, since implementing a YOLO-based controller would depend too much on the pose and lighting conditions. This doesn't ensure a stable response. So SSD offers a bigger robustness, paying the price of a higher inference time. The second neural component of the neural pipeline was the face detection network, called FACED. On this graph and table, it is compared to the classical approaches in order to detect faces, which are the hard features classifier, a cascade classifier. This graph shows that on the same video sequence, the hard cascade solution is slightly more precise than the faced one, because it is constrained to be a square region. However, the faced solution achieves a slightly higher detection rate, raising the 34% rate of the hard cascades up to almost a 37%. So this is more valuable than the better shaping fitting of the hard cascade ones. The last network of the neural pipeline is the face recognition one. Both the graph and the table show that for the same video sequence where two persons appear, a reference face is provided through a static image. And in the video, the evaluated video, two persons appear. One of them is the same person that the one which appears in the reference image, and the other one is not that person. Now, this graph shows that the FaceNet networks yields a lower distance to the reference face when the evaluated face belongs to the same person than if it belongs to another person, which is the orange line. So this behavioral is constant through across all the sequence, and shows that this network is trustworthy to be a method to determine if the reference person is the one which is appearing or not. The last experiment was used to assess the optimizations, the mention optimizations using TensorRT. One of the consequences of improving a graph, of optimizing a graph using TensorRT, is a loss in the precision. Another impact is in the inference time, and these both two impacts are measured in this graph and this table. On the left graph, we can see the intersection over union of the TensorRT boxes with the standard network boxes. So if the loss is higher, if the precision loss is higher, this intersection over union will decrease. However, it can be seen that the intersection over union remains constant, practically in 1. So the optimized networks yield practically the same bounding boxes that the standard neural networks. The shape, the fitting concretely is on a 99.7% of intersection over union. So practically the results are the same. However, in the inference time, we can see in the right graph and in the table that the TensorRT graphs require a much lower time to infer over an image than the standard graph. So we can see that here that using TensorRT allows to reduce the inference time more than 3 times the original inference time, and the precision is practically the same. This means that the resources are efficiently used, and this is a key factor when a portable platform is used. So a typical execution of this algorithm of the full system can be seen on this video available online. We can see a portion of the video in fast forward where the person shows the face to the robot recognizes this person as the reference one and starts following it. And the robot, when it has confirmed that the person is the reference one, doesn't need to see the face anymore in order to follow the person. We can see that if the person is backwards, the robot will follow it. So the conclusions of this work is the accomplishment of the outlined objectives. A real-time following behavior has been achieved, as it has been shown in the video, using affordable hardware, which is practically educational platforms, and a robust detection has been achieved using deep learning techniques, and additionally the softness has been enhanced using an optical tracker. So this has been the presentation of our developed work, and thanks a lot everybody to listen to us. Goodbye.